All right, everybody. So this will probably be the last video for today, but I plan on making another one on to extend this topic a little further tomorrow. But for now, let's talk about the second derivative and how we can use it to find maximum and minimum points on the curve. Okay. And before I do that, this will be important because we'll do so. I'll have an entire assignment devoted to just application problems like this. And what I mean by that is, say we have curves or functions that track seasonal profits or revenues or costs or something like that. And I say it that way because this is business calculus, okay? Then we may want to find minimum and maximum points on those curves. They're of obvious interest to us, okay? To maximize profits, to minimize costs, and those sorts of things are definitely of interest, okay? So that's where I'm ultimately headed with this. For now, I'm not going to bring any applications into it and just talk about how we'll apply the math. So suppose that we have a curve and we want to find either the local maximum or local minimum point, okay? Something like this. This point at the bottom is a local minimum. This point at the top is called a local maximum, all right? Here's how we can do it. There will be a local minimum at some point C on a curve if C is a critical number and if the curve is concave up at C. Concave up meaning it has this shape to it. All right, so those are the two things that have to happen for there to be a local minimum at some point. Now, that's the concept. You got to have a critical number there and the curve has to be concave up there. All right, those two things have to happen. As far as the math for each of those things, I have that in red here. So to be a critical number means f prime c is either 0 or undefined. I don't actually think we'll run into the undefined case in our class, but I'll mention it there just in case. So for x equals c to be a critical number, f prime c is 0. And for the curve to be concave up at that point c, f double prime c is greater than 0. So those are the two things that have to happen. Okay? All right, and if those two things happen, you'll have a local minimum at that point C. On the other hand, for a local maximum, then two things have to happen. There's a local maximum at some point C on a curve if C is a critical number and if the curve is concave down, right, having that shape. It's not enough just to be a critical number in either case. The curve has to have this shape to it of like this for a minimum or like this for a maximum, okay? So, all right, critical number, concave down, local maximum. The math is that f prime c is 0 to be a critical number, and that f double prime of c is negative or less than 0 to be concave down. Okay, so that is also called the second derivative test. So just in case that's referred to in some of your questions or something else you read, the second derivative test is what I have on this first page right here. The two conditions to find either a minimum or a maximum. Now let's do an example. So I have my curve here, x to the fourth power minus 98x squared, okay? And I would like to find all critical numbers there are and all local maximum and minimum points. And it should just come down to this, okay? Here are your two conditions in each case to find a local maximum or minimum. So I divide this problem into parts. So let's say part one, it starts with the critical numbers. In either case, you had to know that there was a critical number at a certain point for it to be either a maximum or minimum. So I find the critical numbers, and that involves what? The derivative being 0. Okay, so if I was thinking ahead a little bit when I was doing this, then I would need to solve f prime x is 0 to find the critical number. So at first I found the derivative, all right, and I get 4x to the third minus 196x, okay? And then I set that equal to 0, solved it. I solved it by factoring, and I got 0, 7, or negative 7. Okay, so I got 3 critical numbers. All right? Okay, now, what was the other condition? I've got the first part satisfied either way. And I don't know if I'm going to end up finding a local maximum or minimum, but I know I've got critical numbers at this point. So if I knew that the second derivative was positive, or if I knew that the second derivative was negative at those critical numbers, then that would fill in the rest of it for me. Then I would know if the curve was concave up or down, and by extension, whether there was a local maximum or a local minimum. Okay? So what I'll do next is I'll take these critical numbers and I'll plug them into the second derivative and I'll see what kind of number I get. Okay, so I'm going to call that part 2. So I have a few things going on here in part 2. Here I'm finding the second derivative from the first derivative. Remember, the second derivative is just the derivative of the first derivative. First derivative is 4x to the third power minus 196x. The derivative of that is 12x squared minus 196, okay? Which you see here in my table. And what are these numbers? What's negative 7, 0, and 7? Those are my critical numbers. Okay, so I take those, I put them in the second derivative, and I see what I get. And I evaluate whether that's a positive or negative number. I don't really care that it's 392. I just noticed that's a positive number. That's all that's really relevant. Why is that? Well, because then I'm finding out that at, say, 7, that 7 is a critical number and that the curve is concave up and that that's a local minimum, okay? So that's what I just found out in this. All right, I put in negative 7, I get a positive number, concave up. I put in 0 into the second derivative, I get a negative number, concave down. I put in 7, I get a positive number again, concave up. So you could think of it like this if you want to. If you're a visual person, some people are really visual, they like to associate pictures with everything as much as possible. So I'm thinking like that's where x equals negative 7 is, you see? All right? It's concave up there. It's like this. It has this shape to it. That's what we're saying. And so, therefore, that point's at the bottom, and it's a minimum. So that's why when I built my answer up, I got a local minimum at 7 and negative 7 because the curve is concave up at both of those points. And then the actual point that's at the bottom is like negative 2,401. And I put that into the original curve and got the y coordinate. So right here, that's a point on the curve, x and y. All right, so this point right here at the bottom has an x coordinate of 7, a y coordinate of negative 2,401. And it's like down at the bottom, the valley right there. Okay, and then I've got a local maximum at 0 of 0 for x, 0 for y. Now again, this right here, that's the point on the curve. This table just tells me whether the curve is concave up or down at those spots, but the actual points are found from the original function. So I don't want it to look like a contradiction that I have 0 and 0 here, but 0 and negative 196 here. Well, we're not using the second derivative to give the point on the curve that is actually a maximum or a minimum. Okay? All right, now, however you look at this, it is just pulled from this part. I find the critical number, I test it in the second derivative. Is it positive or negative? Then I know if the curve is concave up or down. Okay? Now, it might be that sometimes you find a critical number and the curve is neither positive nor negative at that point. Okay? It might happen. You could get 0 for the second derivative and that would not be positive or negative. Okay? And you could get it that it's undefined. So in those cases, you won't have a local minimum or maximum. It's not true that every time you have a critical number that you have a maximum or minimum. It could happen that a critical number does not lead to either. So find your critical numbers, check in the second derivative for positive or negative, define local minimums and maximums from there. If you find a critical number and the second derivative is neither positive nor negative, then that just means that you don't have a local minimum or a maximum at that point. And that could happen.